The art of matrix diplomacy, negotiating eigenspaces with free parameters for perfect simultaneous diagonalization. And our problem today, which is really just an extension of the problem we did last time, A25, is A26, where we're told to consider the matrices A defined here and B defined here. From there, what we want to do is A, verify that they are diagonalizable and that they commute. That should be easy since A and B are both symmetric, as we can observe. B, find the eigenvalues and eigenvectors of A and verify that its spectrum is degenerate. Now this is where it changes from 25, where we had a non-degenerate spectrum. And in C, are the eigenvalues that you found in B also the eigenvectors of B? If not, find the eigenvectors that are simultaneous eigenvectors of both matrices. So because of this degenerate spectrum, we're going to have to do some tweaking in B and C, so brace yourself for impact. So to check for diagonalizability, we need to check for we need to verify normality of these two matrices. Again, normality is sufficient but not necessary for diagonalizability, but it's also quick. And because these are both real matrices, because there's no complex numbers, and they're symmetric, we know that the A is equal to its A dagger or Hermitian conjugate. Same thing for B, so we're good to go on that front. That being said, the normality condition is A dagger A in the commutative bracket. Since we're Hermitian, we get the same thing, and we get 0. We're good to go. Same thing for B. We end up with the 0 here. So once again, evidently, Hermitian matrices are normal. And by the way, so are unitary matrices. So both of those classes are good to go. And since both A and B are normal, we can therefore tell that these are diagonalizable. Now we have to ask, well, are A and B commutative? We need this if we wish to simultaneously diagonalize them. So let's find out. The commutator of AB minus BA, two matrices multiplications, we see that we get a 0, 9, 0, 9, negative 9, 9, 0, 9, 0, which is very weird. We get negative or zeros up in the corners and nines on the main struts with the negative in the middle. But the important part here is that this matrix is this matrix, so we get C minus C, which is 0. So we confirm that they are commutative and we're good to go. Now into the heart of this problem, the eigen decomposition. So again, to get the eigenvalues, we need to use the characteristic equation. And so what we see here is set the determinant equal to 0 of A minus lambda I. Again, must be singular, hence 0. Set up our determinant. We've seen this a handful of times, so we should be comfortable with it. That being said, we end up with negative lambda cubed plus 3 lambda squared plus 9 lambda minus 27. We see we get a bunch of multiples of 3 here, so we can go ahead and factor out lambda plus 3 with the minus sign. That leaves us with lambda minus 3 squared. So as a result, we see that our eigenvalues are 3, 3, and negative 3. Now, since two of these eigenvalues repeat, lambda 1, lambda 2, they're both equal to 3, we know that this spectrum of eigenvalues is degenerate. So that is verified now. But that being said, we know that this is going to lead to redundancies in the matrix equations when we get to the eigenvectors. As such, to determine the eigenvectors, we substitute each of these distinct eigenvalues, and repeated eigenvalues don't need to be substituted in because we will parameterize them out. So, substituting them into A71, the characteristic equation, we see that we have the matrix A minus lambda I times our vector here, the special vector known as the eigenvector. So once we put our lambda 1 in the main diagonal, we see that we just put a 3 in. That'll cover both the cases for lambda 1 and lambda 2, which is how it makes it degenerate, because we end up with the same eigenspace on this one eigenvalue. Nonetheless, what we see is we get another symmetric matrix with negative 1, negative 4, and negative 1 on the main diagonal. And as such, with this equaling or multiplied into the components and all equaling 0, this is a homogeneous system of linear equations. And you guessed it by now, we're going to solve it with Gaussian elimination. So to reduce this matrix, we got to get this negative 1 out of this first component. So divide by negative 1 to all terms of R1. Now we see that row 1 is a duplicate of row 2 by a factor of 2. So take row 2 minus twice the components of row 1 and set that equal to the new row 2. That gives us a row of zeros, as we see here. Note that row 1 is also a negative multiple of row 3, so add them together, set that to the new row 3, and then you see we get 2 rows of zeros, so those two values were redundant. As such, this gives us 2 free parameters. And this says, though, that 1 times A1 minus 2 times A2 plus 1A3 equals 0. If we solve for A2, we get that 2A2 is equal to A1A3. So in this setup, we're saying that A1 and A3 are the free variables, and as such, that corresponds to the two 0 rows. So we're good to go, but normally we only have one free variable, and we set that to whatever parameter value we deem necessary, whether it's I, negative I, plus 1, minus 1, whatever we deem necessary or easy. That being said, now we have to set this for two distinct free parameters. And so we're going to set alpha 1 equal to, or A1 equal to 2 alpha, A2 equal to 2 beta, just to make sure that we're all 2's here. Note that this 2 is going to end up canceling with this 2 once we go ahead and do the math on this, substituting in A1 and A3, factor out the 2, they cancel. So now we have an expression for A2 that is linear and unscaled with respect to alpha and beta. Therefore, our general solution now takes the form of 2 alpha, alpha plus beta, 2 beta, and then we can see that we can decompose them linearly. And now we see that we end up with this kind of crisscross style going on, 2, 1, 0, 0, 1, 2. So naturally, we're going to want to make alpha beta into terms of 1/2 to get 1's in there. As such, let's go ahead and let alpha equal 1/2 and beta equal negative 1/2, which, let's take a note of this. This is saying that we're letting alpha be equal to negative beta or vice versa. However we choose to do this, when we plug these values in, we see the 2's cancel, positive 1/2, negative 1/2 cancel, 2 and 2 cancel, leaving us with a vector of 1, 0, negative 1. But this is only one vector, but we have two eigenvalues to deal with, so we can set another range of values for the free parameters. So here we're going to let alpha be equal to beta and both be 1/2, and then we see that instead of this canceling out, it adds to 1. The 2 and 2 cancels, 2 and 2 cancels, so we have 1, 1, 1. And as we see, pretty darn similar there, except for all 1's. Now, we could repeat this for the other eigenvalue, and when we do that, we get a general solution for the other eigenvalue in terms of, this should be V3, excuse me. That's V3. Must have copied and pasted it wrong. So V3, in terms of the components B1, B2, B3, substitute in that one free parameter. We see we get this, so clearly that's fine. Just let B3 equal 1. Gives us V3 here, which is 1, negative 2, 1. So we have all our eigenvectors. Now we have to summarize this after we normalize them, and then see if these are actually eigenvectors of the second matrix as well. So of course, being a quantum mechanics appendix, we have to normalize these. So let's get to it. What's interesting here is that these are the same form of normalizations that we had for A25. So there is a similarity between the matrices from the number 25 problem and this problem. Pretty darn cool to see. Also pretty creepy. That being said, our summary table is down here. For lambda 1, 3, we get V1 normalized with root 2, 1, 0, negative 1. Then our second eigenvalue of 3, we get a normalization of 1/3, 1, 1, 1. And then our last lonely one that seems to be forgotten is the negative 3, which gives our own distinct eigenvector. Now we have to get into the fun part of this question. Simultaneous eigenvectors. Well, we know that to be an eigenvector for one matrix, it had to satisfy an equation. Same thing for B. So to demonstrate that these vectors are also eigenvectors of matrix B, it is necessary to verify whether they satisfy the eigenvalue equation. So go ahead and sub that through. We see that matrix B multiplied with the vector 1 from our A vectors with the normalization out front leads to a 0 matrix. So that's pretty cool, or a zero column vector. What this tells us is that this is all a constant multiple of 0 here. So that being said, we can write it as 0 v1. So we know that one of the eigenvectors or eigenvalues is 0. Run that through for v2. 1, 1, 1 here, multiplied into the B matrix with the normalization out front. We get a column of all threes. This tells us that we have 3 as the eigenvalue. And once we factor that out, we can compact it back into the vector expression. Run it through for our last one. We see that 1, negative 2, 1 gives us a magnitude of 6 greater in this whole vector column. So factor 6 out. That tells us that our eigenvalue is 6. So evidently the eigenvalues of B are 0, 3, and 6, and that is in the PDF. Good to go there. And again, for the patrons, all the work is in the PDF, all the little nitty gritty of it. But now what this says is that they do share these specific eigenvectors. And since they do share eigenvectors, we can construct the S inverse matrix for the similarity transform where both matrices are diagonalized using the same similarity transforms. That's what's nice about the eigenvector landscape, because if it works for one vector or one matrix, it can work for the other one. We don't need to create a new similarity transform, and hence simultaneously diagonalizable. Very, very cool. Things that don't look at all similar, well, guess what? They are, thanks to these eigenvectors. Now we have to talk a little bit more about why this ended up working in the first place. While these were a lucky guess, so to speak, or a lucky consideration of free parameters, the most general eigenvectors of A are not, with the eigenvalue of 3, is not an eigenvector of B. And the reason why is because if we look at that general solution form for the lambda equal 3, we saw that we ended up with 2 alpha, alpha plus beta, 2 beta, and when we multiply these in, component-wise, row to column, row to column, row to column, row, 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 column, 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 we see that the matrix multiplication doesn't pan out well. In fact, we get cancellations here. We have 3's on all our alphas, 3's on all our betas. After simplification, factor out the 3. But although we remain this value here, we can't say that it's just a scalar multiple here of our original vector without applying some of these fundamental tweaks. Now, this becomes a place where you can be real creative with how these tweaks apply. What we note here is that the middle line does indeed work for lambda equal 3. But if this works for lambda equal 3, then this tells us that the top line or bottom line, that for beta has to equal alpha, regardless of how we want to work it. And we see that if alpha plus beta, in order to equal to alpha, alpha has to equal beta. Or if we want alpha plus beta to equal 2 beta, we see that alpha equals beta once we minus the betas over. So either way, we get this conclusion that beta has to equal alpha. Similarly, we could also ram this down and say that these two could be equivalent if we allow beta to equal negative alpha, at which point we can get some nice cancellations and substitutions for that middle element, so we're good to go. But either way, these tweaks of the parameters were needed. Now, this went through a little bit more of a mess than I had originally wanted, so I also made a secondary PDF where we just kind of use the normalized, or not normalized, but the normal free parameter estimations, solve for one of the components, and then namely A1. So there's another way to do this in the parameter space, and that's what I will upload to Patreon as well for more perspective, because sometimes doing it the way that the author has in the book, especially in some of their examples where they're missing a lot of steps, that's not necessarily the best practice, but the one that they're most comfortable with. And the whole point here is for you to get comfortable using a lot of different angles of approach. So supplying more angles gives you more tools to choose from, and you can figure out what's best for you based on what's needed, and know that that toolbox is available for you. So that will be posted, and you will have that for your library of fun toys of mathematics. That being said, pretty quick video since we set the foundation hard in A25, so that'll be awesome to see complement this. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There is so much more to uncover, and I'd love to have you along for the journey. I also want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting this channel, you can join our Patreon community by checking out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.